Hello, this is the next video, and I'm going to call it Unproven Statements from my Fourier series. This one's from the 11th video in the series, where we assume that this integral, or this function, is integrable in the domain of 0 to delta. And what that means is, and the tricky part is when you approach 0, these denominators go to 0, so how does it behave? Does it go off to infinity, or does it approach a limit? And if it approaches a limit, that means we can integrate it, that it behaves nicely. And so part A, there's two parts to this video. We're going to show that this function does exist, which kind of helps complete my video in Fourier series, the 11th one. So if we look at this integral, there's no problem for some delta greater than 0 to pi, because then each of these are integrable, and they're not 0. So this function is integrable. But it's just when we go from 0 to delta is the issue. So we need to examine the limit of this function as t goes to 0. And we'll combine this fraction into this. Then as t goes to 0, everything's continuous, but we get a 0 over 0 case. So we can use L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator, and we get this. And when you put in t equals 0, here you get 1 minus 1 is 0. And you get 0 here, and the t right there, t over 2 is 0, so this is 0. So you get a 0 over 0 situation again. So we use L'Hopital's rule again on this numerator and this denominator, and we get this. And then when we evaluate it at t, this is 0, but this is 1/2 plus 1/2, which is 1, and the numerator is 0. So we get 0 over 1, which is 0. So this function limits to 0 as we approach 0. And since the limit exists, that means that function behaves nicely, and this integral, it's going to be integrable, so it does exist. Now, if we were to plot this function here, it does look like this from 0 to pi. So as you approach 0, it does behave nicely and goes to 0. So then we can integrate this, and it looks, whatever it is. So the second part in video 11, we looked at the remainder, which is the nth partial sum of the Fourier series minus the function we want to estimate. That's the remainder, and we said that it equals this, and then we did it without proof. In video 7, we gave several formulas for the remainder and also the partial sum, but not this one. I said it's a straightforward U substitution. So now we're going to prove that. And so from video 7 in the Fourier series, we showed that the partial sum, the nth partial sum of the Fourier series, can be written like this. Okay, so for that proof, you'll need to go to F7. And then for this, if we do let t equal minus w, and then take the derivatives, substitute it back in, we get this. Now, this is not quite that. The limits are reversed of what we need, but if we take this minus into that, we can reverse those. And also the Dirichlet kernel is a even function, so this minus w is the same as just w. Okay, so then we get this. So the nth partial sum can be written like this. Now from F11, which is the Dirichlet kernel, we said that we can take the derivative of the Dirichlet kernel from minus pi to pi is 1. And notice that this isn't in the t world. So that if you were to take that out and then integrate it, it's once. You're taking 1 times f of x. But the reason we do it like this is because it kind of looks like this one. So we can take the difference of those. So combining the results, we get the residual, or remainder, is the nth partial sum minus f of x. So the nth partial sum, in this video we showed it was this, which is this part, and then f of x can be written like that. Now, integrated over the same range, and there's a lot of things common, so we can combine them, factor out the Dirichlet kernel, you know, there's a pi common, it comes out, and we get this. And this is what we wanted to show, and this is what I stated without proof in that video. So that's all I have for today. Hopefully you enjoyed it, and subscribe and so you don't miss the next one. Thank you, bye.